Thanks. Good morning, everybody. Yeah, I'm glad to have the chance to deliver a lecture on the physical geology of Taiwan to you this morning. And I will separate it into three parts. First, before you going on to the subject, the main subject of today, we would like to introduce the basic theory, the plate tectonics, for the first part. Second, the main body, the physical geology of Taiwan. And I would show you the historical development of the island of Taiwan, its tectonic evolution, and particularly in series of pictures to illustrate all the processes. And finally, there's a film in DVD and top of East Asia, and mainly deal with the geology of Taiwan in various aspects. So in between, you have two stops for rest of 5 minutes or so, and you may have various questions. So shall we start? Okay, and let's move on. Here's a satellite image of the Middle East and northern tip of the Red Sea, and you can see the land, the Africa and Asia have been separated by this narrow strait. And here's the Suez Canal, was built in the 1950s. Okay, here we all see a lot of earthquakes and a lot of natural hazards in the island of Taiwan, but this is a worldwide phenomenon. And first of all, we live on the lithosphere. That means a layer of solid rock of more than 100 kilometers in thickness. And this lithosphere has its own density and its own constituents. So why is on the surface of the Earth? Because it's lighter than the material beneath. And this thick lithosphere overflow on top of the asthenosphere, which is hot and dense. So whenever there's some physical material like glaciers loading on this surface, and there's a bend, so and afterwards deglaciation, this piece of land would be rebounded. For example, in North America, you have a lot of so-called Lake Superior, a lot of Great Lake area. Those was sculpted and was formed during the glaciation. Now the glacier is gone. So a piece of land, particularly in the Hudson Bay in Canada, the land was rebounded. For example, in Western Europe or Northern Europe, Norway, Sweden, or even Great Britain, in particular in Scotland, there are a lot of places have been rebounded. So if you live in a seesaw area, you feel that within a decade or more than 100 years, the soil line has been upraised. So in comparison speaking, the sea is in subsidence. So this is the simple as that. And this so-called lithosphere, like floating on the mantle, or you call it floating on the asthenosphere. And there's a great difference between the piece of lithosphere in the continent as well in the ocean. So you can see that the thickness of the lithosphere is much greater in the continent than the ocean. The reason for that is constitutes a lot of lighter material, and this is the denser material. I would like to introduce some of the main chemical composition for the material within the lithosphere. It's mainly composed by 8 elements. For example, silica, oxygen, aluminum, sodium, potassium, iron, magnesium, and calcium, if I've said. So there's a so-called, these are major elements. Of course, oxygen and hydrogen. major constituent of the lithosphere. The difference between the lithosphere and the asthenosphere is in density, because in the oceanic lithosphere, you have the more denser material, like for example the iron and magnesium, compared speaking your lighter material, silicons, in the so-called lithosphere. So the buoyancy or the uplift power in the continental is much greater than the oceanic lithosphere. For example, if ice. So we all know that pure ice have a density of 0.9 or 89, something like that. Because there are a lot of bubbles, we've been trapped inside the ice. So a rough estimation would be 82%, the iceberg on top of the ocean. Okay, you have this kind of analogy for looking. So these thick layers of lithosphere was separated into the plates, so-called, and the plate in motion. And the motion is so-called plate tectonics. So whenever there's a motion against this plate, that means that they are crushing or collided to each other, earthquake occur. Or the movement of this plate are gravitated away from each other, the pulling apart, like the mid-ocean ridge in the Atlantic. And this area is the boundary of the plate where the plate move away from each other. In the Pacific, we have seen that this dotted line, Sumatra, Indonesia, and then you have the small triangular facet, right? Triangular rhombic shape here is a Philippine Sea plate. And this boundary is a kind of so-called convergent boundary, where two plates met together, they are heading it to each other. And this have a great significance of the world, because more than 90% of earthquake along this plate boundary, because the relative plate motion. Another example would be in California, you have the Pacific plate moving northward or northwestward and northwest, and then you have the St. Andreas Fault right here. This kind of boundary is more or less a kind of the so-called stripe-stepped fault, means like the in a row, two directions, and then they're so side by side, but heading on opposite directions. There are no conversion or diversion in between. So this kind of stripe-stepped transformed fault. So there are two types of convergent boundaries. One is convergent, divergent, or I would say free. Another one is the so-called transform or stripe-stepped components. So here's a look, a transition between the ocean and the continent. So the continental margin, or continental shelf. And then you see the deep ocean, the Pacific Ocean or Atlantic Ocean. The mean depth is about 5,000 meters for the water part. So you can see the transition zone between the continental margin, continental shelf. Yeah. So for North America or Europe, in the North Atlantic, both margins are this tight, so-called have a large continental shelf. Yeah? For example, in Brazil, offshore sail more than 500 kilometers, and the water depth is still very, very shallow. But in the Pacific, off course of the Taiwan, you have deep trenches up to 6,000 meters, or a few tens of kilometers. You have go to the bottom of the ocean of 4,000-5,000 meters already. So this kind of plate configuration have a great topographic influence on the surface of the Earth. Here is the seismic zone around the Earth. They are mostly in around the so-called plate boundaries. because the plate had moving gravity to each other. Some tear apart, some collide to each other. So three types of a boundary would be looking at here. You can see it. The important thing for the pulling apart is that the hot material of the asthenosphere is coming up to the surfaces as the overpressure have been gone, because they tear apart this part a lot of space and then create a lot of cracks, so the magma coming out. So for in the mid-Atlantic Ocean, there's a line or igneous extrusions on top of the seafloor. Also a lot of basalt. This extruded material, the magma, cooled, forming the basaltic rock spread around the seafloor. And in the convergent boundaries, we have there are two situations. One, we call it subduction. That means one plate can override the other plate. This is the where two plates met together. The other configuration would be the so-called collision. In two plates do not subduct or overriding each other. They just a head-on collision. So the mountain ranges of the world were formed by this kind of convergence. Himalayas, Alps, Taiwan is called the mountain building process. Is mainly by the collision of the two plates. The other one is like the driving a car on a double lane or to one direction, the other direction. Because the boundary is not a straight line, so there's a curving, and when these two plates move together, the protruding part or retreating part will hit each other, create earthquake or other deformation along this fault, so-called the fault zone, the transform fault between these three. So still there are earthquakes, the same as here and here. But anyway, in sum, the fracture or the fault created in this part is extensional, and the part right here is contractional. Right here, you may say transform or strike-stepped in nature. And here, an animation showing the so-called divergent boundaries. Plate move out each other, and new ocean lithosphere formed. And you have another convergent boundary. Because the oceanic plate is heavier, denser, so whenever two plates meet or head on to each other, usually the oceanic plate sinks. There's quite a bit of thing happens at this kind of boundary. So I will show you another animation for the maybe later is better. Is anyway, that's an interruption for this. Okay, you get the beginning, and then the final. You have the ocean. So before the time one, plate A and plate B actually is one plate. So rifting occur and then forming the oceanic material, and then the oceanic plate as time flows by. So for South Africa, you have heard that there's a Great East African Rift. That means Ethiopia pulling apart away from Congo or the central part of Africa, start to create an ocean between these two parts. Yeah. So that's one of the phenomena in the world you can see. And you can see another. So for details, the extension tear apart plate on top, you can see the magma coming out right at the bottom of the seafloor in the deep So and here is a magma chamber, and you have a lot of vertical fractures filled with this so-called magma. So-called we have the dike, and because they align in the perpendicular orientation, they're the sheeted dike. And then you have the pure lava or the basalt on top of seafloor, and then you have deep sea sediments. So it's kind of trinities: the mantle, the ultramafic rock, and the basaltic rock, and then the sediments on top. So whenever inland you find this kind of trinity or this combination of rock strata, no matter in the central Mongolia or in Tibet, you realize that this kind of rock was formed in the mid-ocean ridges, or in particular places that the ocean have tear apart. So remember this. And then forward. So yeah, so you can see that the configuration of all these three. So the Atlantic Ocean move apart at the rate about 10 centimeters. It varies a bit per year. So in a minute of time, you have moved away 10 kilometers. And this, the width of the Atlantic Ocean, if the rate continues like this for millions and millions years ago, and you trace back in time, you can see that the width will be divided by the rate. So Atlantic Ocean, the age of the Atlantic Ocean, and then you can get a good estimation. And on top of that, you have see that if you drill a borehole into the ocean, you can find the age varies. From the middle is youngest, so it's newly created, and away from that to the margin or ocean will be the oldest. So a lot of oceanographer and geology has to do this. In the mid-ocean ridges, because the magma coming out, and the cold water is cool, usually 4, 5, 6 degrees in the bottom of the ocean. And a lot of interaction between the hot material and the cold water. So forming a lot of black smoke. And actually, because this hot material, hot fluids are very corrosive. So a lot of material within the basalt, a lot of metals or other rare metals have dissolved in this hot gaseous fluid, and then they cool down, and then all the dissolved material have precipitate rinding around the pipe, hot pipe here. So for a long period of time, then there's a lot of mineral deposits around this spot. Yeah, here is the age distribution of the ocean. You can see that. Yeah, numbers are the million years. So you can see that Jurassic, Cretaceous, where the dinosaurs lived happily, and then the Paleogene, Eocene, Oligocene, Miocene, and Pleistocene to present. You can see the distribution, the age of the ocean. Yeah, and so before is in the more or less the same place. Yeah, this tells you some of the physical properties of this pressure flowing on the ocean, and then you have because it's denser, so it's easier to sink down for the oceanic plate. And okay, let's take a profile of this. What happened to this subducted material? Because this oceanic plate composed of the surface ocean, deep ocean sediments, pure lava, all this contains more or less a lot of water within. So the rock, the plate, the oceanic lithosphere subducted beneath another plate, and this water had reaction with the other elements or other minerals, like I just mentioned to you, the silicates, a lot of rock-forming minerals, quartz, feldspar, mica, and all these. Then this rock would be into the state of molten material. Yeah, everybody have been doing some cookings. During cooking, one constituent is very important. That's water. You boil it, you fry it. Even you fry in the oil, the food you are cooking have certain amount of water within, no matter it's with meat or vegetables. Yeah. So because the water, when you heat it, you vaporize. The water expands, and this vapor have a very can dissolve. Loss of the dissolving power is much greater. So things happen to the rock. So you come down, the pressure building up, but temperature as well. You can see the profile of the temperature is increasing down to the core. Anybody tell me what's the temperature of the core of our planet Earth? Give me a figure. 1,000, 2,000, 3,000, 3,000 centigrade? About 5,000 or something. Okay. So anyway, long before that, magma formed. Depends on composition. If you are granitic, so the magma would be a granitic magma. If about 600-700 or something, that would be with wet rock, you can form magma. If the basaltic more so-called a lot of iron or magnesium, then the magmatic temperature would be much higher, so it would be 1,200 centigrade. That means that this slab will sink deeper without magma. So once a magma form, that is the density is lighter than the adjacent material for the upper mantle, so it rises. You see a lot of dotted line here. It means the boundary between two constituents is detected by seismic waves, because the vibration of different material, different density, would give you a different frequency of waves. So at various depths, you realize that the constituent of the material down beneath the earth varies. Okay, here you can see that everything almost activity on Earth could be explained in this profile. And we have the subduction and so-called forming and the magma forming, uprising, and from volcanic islands or volcanic on top of the surface. The alignment or the surface alignment of the volcanoes could be separated, whether it's the ocean island formed by the hotspots where the source is very deep, like Hawaii or Iceland. The other, like the chain of volcanoes coming, like the eastern Taiwan, you have a chains of volcanoes, Yilan, Lütao, Patan, and northern Luzon, and form volcanic chains. So all these are because the interaction, the movement of the plate relative to each other. And here is seeing the more complete processes, and the surfaces were subducted, create a trench here, but the sediment was squeezed, so the material is coming up right here, so-called, and this is deep ocean, so-called before the arc, so we call a four-arc basin right here, and the material from the surface of both plates accreted to each other, so we call this kind of constituents called so-called accretionary prism, and subducted material between arcs. When this is forming a lot of topographic height on top of the surface of the earth. And here analogy here. For example, right this part. If the plate push to each other, moving to each other, then have a lot of compressive forces. A good analogy would be the like this pile of sand or snow pulling forward. So the surface right here is the free surface. And then, so we push the material would move to the less pressed place. And then you can have this kind of configurations moving forward, or even things moving backward. That's interesting for the Taiwan island. You will see that actually it looks like these configurations later. And here's give you some subduction processes. The continuation of former the emanation. So this is going on and on around the Pacific Rim. I mean in the East Asia, South Asia, North American, South American. All this rim, Pacific Rim, is this kind of so-called subduction, or either subduction or collision, means the convergent boundaries. Yeah, so you can see that in diagram like this, all the transform movements. So in the mid-ocean ridge, we have the two pair apart, but there's interesting features in the mid-ocean ridge. Not only the north-south direction of major so-called rift zones, but there are zones in the perpendicular to that so-called stripe-shaped or transformed movements. Yeah. So yeah, he's he just go into more detail. So just left it, but when it's in this way, you see the emanations. Yeah, for this. So that's why the mid-ocean ridges align in a zigzag pattern, not a strict opening or cracks or opening of the crate. So, see here is I think it's a view from Mount White or Mount Rainier in the Washington State. The Cascade Mountain Ranges, and further to ocean is the Olympic mountain ranges in the northwestern American. It's a great dike. Yeah, because these dike rock are resist erosion, so it's protruding above the surface. And here shows another type of the pay boundary. Yeah, we have said that the three types of pay boundary, the stripe one. Actually, there's some oblique situation between the two places. For example, this so-called Great St. Andrew Fort is a kind of stripe slip. Also, because convergent direction is something like this and this. So there's not actually purely a stripe slip. At the places there's transtension, at places there transpression, because the boundary is curved. In some places it's open up, in some places it's compressive. Here is the aerial photo of the St. Andrew Fort. Yeah. Looking nice, not a straightforward, but curved. Yeah, but has shaped the geographic landscape a great deal, a great influence. Okay, the other one is the hotspot, where the source is came from the core mantle boundaries, very deep, at least 3,000-4,000 kilometers beneath the Earth, the hot material coming up. So you can track that on the surface of the Earth, because this hotspot lasts for million or tens of million years. So the plate move every year several centimeters, and in the meantime move 10 kilometers or a few tens of kilometers. Then you date the rock, volcanic rock at here, you can see that the hotspot was situated here, and the plate moved away or move in the other directions. For example, in Hawaii, that's very interesting. You can see that the track of this so-called hotspot, the volcanoes, the chain volcanoes, sometimes it changes direction. Means the plate movement is not fixed for certain. Is not fixed for all the time. It sometimes is moved to this direction and then change shift. I would like to suggest that there's a great reorientation of the Pacific Ocean during Eocene, Oligocene time. That means 20 to 30 million years ago, the plate was moving in this direction, but later this way. So this will help you to build up the history of the ocean. Yeah, and the trenches. So at the seafloor, you have seen a lot of mountain ranges in here. So I think I would more or less stop here for the first part of the introduction of the plate tectonic. Let give you a background of what happened on the surface of the Earth. Here's the example of the Hawaii chain islands.